Hi guys, it's Sekiso once more, man. Hey, we are doing a chapter that I normally don't like. Not like in the sense that I'm running away from it. Normally, if you are a student, you do a lot of mistakes on it because there are a lot of angles involves definitions, and if you don't know definitions, normally it's highly unlikely that you might even be able to attempt this. But let's go on. Let's go on. Our friend has sent this problem, and he's here as well today. He really wants this problem to be done. I don't know. He said at least some of the exams are postponed, but I won't go higher than that. Uh, they say a three-phase 132 kilovolts. That's very, 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 very important. This is not a short because of the voltage. Remember, from a 0 up to 20 kilovolts, I will say it's a short line, and normally we will use wooden poles or steel poles or concrete reinforced poles and so on. But this 132 kilovolts is a long distance transmission line, and we have to use what is so called lattice towers and so on. So this is just a section of a transmission line. We are yet to discuss the type of conductors. Maybe you hear from the first video on transmission lines that you have to go uh, compare copper and aluminium and come with a decision as to which one you should use. Even the aluminium itself has its own shortcomings. That is why sometimes you may find it has to be reinforced in order for it to be more flexible in transit. Remember, it is only aluminium, it's only 60% conductive. Copper is an ideal material for the transmission of electric power. Aluminium can only conduct 60%, but there are things that are to be done on it in order for it to meet the requirements of copper. It's an obvious reason. We can't use copper because it's expensive. People will steal it. Number one. It is non-available. Remember, if you work for a certain company, the main purpose of that company is to make money. So copper is expensive. They're gonna kill you or even fire you. Who knows? But this is a long transmission line, and then 50 hertz overhead line has the following constants. By constants, we mean parameters. What are the parameters of a transmission line? We've got the resistance and we've got the reactance. What are the reactance? The reactance is capacitive reactance and inductive reactance. Those are the parameters of the line. And then, of course, we've got the resistance of 16 ohm, the inductance of 127.32 millihenry. We're gonna use this inductor to calculate what? The inductive reactance, and this capacitor to calculate the capacitive reactance. And we say the line supplies a load of 80 megawatts. This is at the receiving end, at a power factor. This is the information from the receiving end. And you are asked using the T method. This shows that it's a very, very long transmission. If you see T method or pi method, then you know this is a long transmission line. Because of the voltage, it goes there. Now, they say calculate the sending end voltage. But first of all, let's calculate this. You remember, in a short line, there is no capacity. There is no capacitance. Why? Because the line is very short. Therefore, the capacitance is not brought into play too often. But in a long transmission line, it has to be brought into play. And normally, it is lumped at the center of the transmission line, while the inductance are normally lumped on either side of the transmission line, and this is the case. This is the case. Because of this capacitor, it means we've got a voltage that can supply that capacitor, and then we've got the capacitive current. Here we've got the sending end voltage, or the sending end station, and then we've got the sending end current. This is half the inductance on either side, meaning this is R over 2, this is XL over 2, this is R over 2, this is XL over 2. This XL stands for the inductive reactance, and then this, it is the capacitance of the line. And then here, of course, we'll have the receiving end voltage, where there we've got the receiving end current. But now, unlike in a short line, the sending end current was equals to the receiving end current. Now, in this case, the sending end current is equal to this plus that. The arrows are facing in the same direction, meaning you add. It's maths, the language of engineering. This is IR plus IC. This is the formula we're gonna use to calculate. This is the formula we're gonna use to calculate the sending end current. And then, if we are to do the vector diagram of this before I erase, guys, it's gonna be the VR, okay, and then say this will be VS there, and then this is VR, and then from here to there it will be VC, and then of course this is IR multiplied by R over 2, and then this is IR multiplied by XL over 2. There are 90 degrees here, guys. It's just that I don't have space. And then here is IS multiplied by R over 2. Here is IS multiplied by XL over 2. So basically this is the case. Now, what does this mean? It means VC is equal to this voltage plus the volt drop. We explain how actually, okay, let me do this so that you can have plus the volt drop. What does that mean? It is a half multiplied by IR multiplied by Z. This is half the voltage drop in a transmission line. And then this is VC, VC. Now VS, this VS is equal to VC plus that voltage drop, this voltage drop, which is half into IS multiplied by Z, multiplied by Z. I think we should be happy with this, guys. If you know your sketch and your vector diagram, you should be able to derive these formulas, not to cram them. Let's march on. I will have to erase, guys. But now you see what's going on here. Right. Someone almost killed me when I say, hey, gents, this channel is actually for youngsters, man. S1, S2, S3. Hey, we are in there. I'm doing what with DMR. You must put me in. Otherwise, head will roll. You are in. Now, let's see. This is a load at that power factor, meaning we can calculate the load current. What is the load current? It is IR. It is IR from the sketch and the vector diagram, meaning power is equal to root 3 V line I line cos of theta, and then of course I line, which is receiving end current. By the word load, we mean the receiving end, the thing that is supplied. A load, the thing that is supplied. So this is 80 multiplied by 10 to the power 6. Why? Mega. The word mega means 10 to the power 6. Kilo means 10. I have seen a lot of problems, but we are yet to end them out. Some people have crammed the units of power. They have crammed meters. What does this? If you know the formula, you must be able to see the units and prove it to me, but we'll do it. Someone said, hey, we must be able to check how to do units and stuff, because if the units are wrong, you are wrong. Over square root 3 multiplied by the line voltage, 132, 10 to the power 3 multiplied by cos of 0.75, and it's equals to what? It's equals to 80 exponent 6 divided by open brackets second function square root 3 multiplied by 132 exponent 3 multiplied by 0.75 closing brackets. Answer, we got 466.5. 466.5. Angle of what? The angle of that power factor. And it is equal to what? It's equal to the arc cos of 0.75. It is minus, there is no minus there, but it is minus 41.41 degrees amps. Why minus? Because it is lagging. If it is, say, a 0.5, a power factor of 0.5 lagging, then the angle of that particular power factor is minus. That's why it's minus there. It's true. It's true, and it's a fact. It's a fact. There should be minus there. Now, we've got this. Let me write it there in case I'm about to delete. IR is equal to 466.5 minus 41.4 degrees. Right. Now then that I've got this, where to now? I've got R. And I'm to calculate what? The sending end voltage. What is the sending end voltage? The sending end voltage is equal to Vs is equal to Vc plus half into Is multiplied by Z. So I've calculated IR. But what is Is? Is is equal to IR plus IC. I found IR. I have to find IC. But what is IC? IC is equal to VC over XC. I don't know. I have to find VC first. Now I've got this. But what is VC then? VC is equal to, from your sketch, you look, just, you can't cram this. This, you derive these formulas and they are found from your vector diagram. That's the only way where you can find them, and I've shown you how. So VC is equal to VR plus half into IR multiplied by Z. We've got this. We can find this. Let's find it. Now, to find this, let's say, for instance, XL is equal to 2 pi FL. And then this is 2 pi multiply by 50 is given, the L is given as 127,32 multiply by 10 to the power minus 3. And it's equals to what? It's equals to 2 second function pi multiply by 50 multiply by 127,32 exponent minus 3. And it's equals to, let's say 40, or should I write it as 39.99? Let's write it as 40 ohms. This is 40 ohms. This is XL, but we want impedance. And then impedance is equals to R plus J40. So R is given as 16 there. And then you've got 16 plus J40 equals to 43,08, angle of second function expansion 68.2 degrees ohms. This is sorry. This is impedance. This is the impedance of the line. Now then that we've got the impedance, we have to calculate what? We've got this, we've got that, we can find VC. Therefore, VC is equal to this 132, where, look just, where there is current and impedance, you always work in phase values. If you are not given, if there is no statement that says a delta what or a star what, it is just like that. But there is impedance and then there is current. You always convert to phase values. You work with phase values. So for that reason, we are to divide this 132 exponent 3 by square root 3, and it's equals to what? It's 132 exponent 3 divided by second function square root 3, and it's equals to 70, let's say 76 to 10,2 angle of 0 volts. Yeah, that's the case. 132 exponent 3 divided by second function square root 3. 132 exponent 3 divided by second function square root 3. Yes. This is the case. Now, this is 76 to 10,2 angle of 0 plus. Okay, let me write that Z there. This Z is 43,08 angle of 68.2, and then I can erase it from here. Right, it's equal to half into the current is calculated as how much? As 466.5 angle of minus 44,41 multiplied by the impedance, and it's calculated as 43,08 angle of 68.2. If you can see something here, guys, just remember what I've been saying, and then, but this is 68.2, and it's equal to what? This is 76 to 10 angle of 0 plus, okay, let's work out this. And the Botmas rule from sub A, you start within the brackets. If you remember, the reason why your sub A madam or mistress, what me or what was teaching you Botmas rule, he knew in future you will be requested to calculate this. At the time you were told not to try this at home, ne? But now it's your time. Let's say it is 466.5 angle of what? Minus 44,41 multiplied by 43,08 comma 08 multiply by, okay, angle of 68.2, answer, multiply by 0.5. This is 148.41. Angle of what? Angle of 23.79. Now we can add this, then we're gonna get VC. It's gonna be 76 210.2, angle of 0 plus 148.41, angle of 23.79. Answer, it is 85,500.93. Angle of what? Angle of 2.72 degrees volts. Guys, remember, if you don't put that 0 there, or that 0 in this phase receiving end voltage, your whole calculations are wrong. Those are some of the pitfalls. That what earlier on I said I don't like this because of it, as you people do a lot of mistakes. I'm one of those. This is the phase value of the capacity, the capacitive voltage. Now then that we've got this, we can calculate what? We can calculate IC, which is VC over XC. But what is XC? From sub A, of course. XC is equals to, okay, I can erase this. I don't think I'm gonna need this. XC, the capacitive reactance, is equals to 1 over 2 pi FC. And this is 1 over 2 pi multiplied by 50 is given, multiplied by the capacitance of, I was gonna need it. It is the capacitive 2.65. 2.65 multiplied by 10 to the power minus 6. The word farad, microfarad, means minus 6. And it is equal to what? It is equal to 1 divided by open brackets 2-second function pi multiplied by 50 multiplied by 2.65 exponent minus 6, closing brackets. Answer 1201.17 ohms. The capacitive reactance is calculated in ohms. Now 85500.93, angle of 2.72, all over the capacitive reactance is 1201. Where did I call? Okay, 1201.17. The capacitive reactance, guys, it is minus 90 degrees. The capacitive, the angle of the reactance is minus 90 degrees. We will do some basics. Maybe don't say, hey, I'm doing S4. Next week I will be doing basics with the N1s and stuff. Just come in maybe and say, hey man, this is the case. You can see maybe where this minus 90 degrees come from. I will do you some those IC and so on, where I have to show you how the reactive power, what causes a low power factor and stuff. But we will play with that. It is a game. It's our next game. Okay, it's equals to what? Let's say it is equals to 85500.93, angle of 2.72 divided by 12 01.17 angle of minus 90 is equals to what? Is equals to 71.18. Angle of what? Angle of 92.72 degrees. This is amps. Now then that we got this, we can now, actually this is what? Oh yes, this is IC. Now then that we've got this, we can now calculate the sending end current, which is IC plus IR. And it's equals to what? IC is calculated at 71.18 angle of 92.72 plus IR. What is IR? 400 and something. 466. 466.5 angle of minus 41.4. And it's equals to what? It's equals to 71.18 angle of 92.72 plus 466.5 angle of minus 41.4 rather, sorry. Is equals to what? Is equals to 420 angle of minus 34.4 amps. That's the sending end current they were looking for, and it is 420. Now the final say. Now we have to, okay, let me delete here. I don't think I'm gonna need this anymore. Now the sending end voltage is equal to VC is calculated plus half IS is calculated multiplied by the impedance is calculated as 43.08. I'm right? The impedance, yes. Now it is 85500 comma what? Comma 93 plus 0.5 angle of IS is 420 angle of minus 34.4 multiplied by 43.08 angle of 68.2 is equals to what? Is equals to, okay, let's work out this first. It will be 420 angle of minus 34.4 multiplied by 43.08 angle of 68.2. Answer multiply by 0.5, and it's equals to what? It's equals to 9046.8 angle of 33.8. Now let's add them together to get the sending end voltage. This is 85500.93 angle of what? You see another mistake. We missed the angle here. What is the angle of VC? It is 2.72. We were gonna be very wrong. That's why I said I don't like this, because there are a lot of mistakes involved. 0.72. This is angle of 2.72. So this is, let's start from scratch. It is 85500.93 angle of 2.72 plus 90 46,8, angle of 33.8. Answer is equals to what? 93,365,9. Angle of what? Angle of 5,5, say 9 degree volts. This is the phase voltage. This is the sending voltage phase value. Let's convert it to line voltage. Vs line is equals to what? You just multiply this by square root 3. Multiply by second function square root 3. It is 93,365.9. Angle of 5,58 multiply by second function square root 3. Answer, it is 1, okay, divide by 123,000. It is 161,71 angle of 5,58 kilovolts. Actually, you have answered everything. The question was calculate the sending end voltage, this one. And then they say calculate the sending end current, this one. And then, okay, and power factor as well. And power factor. Look, the sending end, we are yet to, it can't be this. There's a reason why it can be that. Remember, a power factor, it is the cosine of an angle between the voltage and current. So this is the only current. You are yet to do the voltage. Guys, I'm told my time is up, but I will show you this angle. It is the only one part, and this video is quite long. It's roughly 34 minutes, and I really apologize. Just subscribe, follow us, and then we'll still continue with these transmission lines. We're gonna do, they are actually asked in 5 different types. We will do another 3 of them, and you'll see this is actually very easy. Just master them, except don't concentrate only on the mistake you are doing, but perfection every time. If you do one every day or every after a week, you'll be fine.